and we're going to continue on with Chapter 12 with the topic of alkyl halides. Now, any organic compound which contains a bond between carbon and a halogen is called an alkyl halide. And if you'll recall, please, the term halogen, from which halide is derived, includes all the elements in group 7A. So those would be fluorine, chlorine, bromine, and iodine, of which by far the most important are chlorine, bromine, and iodine. Fluorine is seen in some compounds, particularly polymers, but in terms of the compounds we're most likely to encounter, fluorine is not among those. So the same question I asked for ethers and that I'll continue to ask for the different functional groups would be, what is the strongest intermolecular force experienced by alkyl halides? And let's go ahead and take a look at an example here. We'll look at 1-chloropropane. Well, there are no hydrogen atoms bonded to fluorine, oxygen, or nitrogen, so these molecules cannot hydrogen bond. Now, technically, if there was a fluorine for the halogen, it could receive a hydrogen in a hydrogen bonding situation. It could donate its lone pair, but among other molecules of themselves, alkyl halides cannot form hydrogen bonds. The next strongest intermolecular force is the dipole-dipole force, and since chlorine is substantially more electronegative than carbon, we would expect that these molecules would exhibit dipole-dipole forces. And so those are typically the strongest forces that we encounter for alkyl halides. As these carbon chains get longer, just like for ethers and for alcohols, the dipole-dipole forces become less important, and it's ultimately the London dispersion forces that start to take over as the molecule becomes less polar. So what does that tell us about relative boiling points and solubility in water? It tells us that this is going to be in a similar situation to ethers, where these molecules are not going to have melting and boiling points as high as alcohols. They are going to be lower than alcohols. They are also going to be generally less soluble in water than small alcohols. But because they do have some dipole moment, we would expect them to have higher melting points and higher boiling points than alkanes of a similar molecular weight, and we would expect them to be slightly more soluble, although we find that they're generally not terribly soluble. We've touched on the topic of naming alkyl halides in Chapter 10. Recall that it was mentioned that alkyl halides are not treated as functional groups when we are talking about naming them, so just in that context. And so by that we mean we don't change the ending of the name to match, like for example alcohols having an OL ending. We don't do that for alkyl halides. Instead they are named as substituents. So to the list of substituents we already have, like methyl and ethyl, we add these 4 substituents. Fluorine is fluoro, chlorine, chloro, bromine is bromo, and iodine is iodo. You notice that you just dropped the INE off the name of the element, so chlorine, and it becomes chloro. So let's go ahead and practice naming these compounds right here. I'm not going to have you stop the video this time. We'll just walk through it together. So we go ahead and we look here. And remember, these are not functional groups. Chlorine is just considered a substituent. So if we go ahead and take a look here, we want to number the longest chain such that we get to the first substituent as soon as possible. So if we start from here, 1, 2, we end up with a substituent on carbon number 2. If we go this way, 1, 2, 3, the first substituent's on carbon number 3. So 2 would be better, so we are going to number from the left there. We have 2 substituents, a chlorine atom and a methyl group, and the parent with 5 carbons is pentane. So we list the substituents alphabetically in order. So chlorine, a chloro group, then methyl, and then we state the name of the parent hydrocarbon. So the name of this compound is going to be 3-chloro, 2-methyl, pentane. Again, remember there is no dash between in front of the parent hydrocarbon unless you have to indicate a functional group. There is no functional group, though, for naming purposes. Over here, we have a cyclopropyl group, and on that cyclopropyl is a bromine. So we're just going to name this bromocyclopropane. Again, there's no reason to number this because with one substituent, the substituent is always on carbon number 1, unless there's a functional group. Thiols are a functional group which contains the sulfur hydrogen group here, which is called a sulfhydryl group, but I don't need you to know that term. We often call these sulfur analogs of alcohols. Let me explain what is meant by that. An analog means something is similar, and so all this is saying is we've taken an alcohol with an oxygen there and replaced it with a sulfur. However, this presence of the sulfur does have a dramatically different effect on its reactivity, its chemical properties, its physical properties. Probably the most familiar property of thiols is their intensely unpleasant smell. While that isn't going to be true for every thiol, it is certainly a common feature of all the smaller thiols, the ones with low molecular weights. For example, here we find 2 of the 3 small thiols which are encountered in skunk spray, which of course give it its intensely unpleasant smell. You'll notice that this is a trans compound while we're taking a look at it because we've got 2 hydrogens on opposite sides. Now, I'm not going to be worried about naming thiols. It's a group I will leave off. In case you're curious, you can probably just figure it out from here. It's a simple matter of appending the word thiol to the end of the name and indicating the position of the thiol with a number, but not something you have to worry about learning. We're going to look at one important reaction of these when we get to oxidation and reduction reactions shortly. But for the time being, we're just going to continue on to the next set of functional groups, which include aldehydes and ketones. These 2 functional groups are typically grouped together because of their similar reactivity and similar structure. We know that both of these contain a carbon-oxygen double bond. For whatever reason, these 2 functional groups are covered in Chapter 12, while all the other functional groups which contain carbon-oxygen double bonds are included instead in Chapter 13. Now, the main difference in their structure is the fact that with a ketone, the carbon, in addition to its double bond to oxygen, must be bonded to 2 additional carbon atoms. With an aldehyde, it must have a bond to 1 hydrogen, and either 1 hydrogen, of which there's only one way that could happen, or a carbon atom. Let's again examine intermolecular forces. The most important intermolecular force for aldehydes and ketones. Again, neither of these groups can form hydrogen bonds with molecules of exactly the same type. They can hydrogen bond with water, owing to the lone pairs that are on the oxygen atom, but again, they are only lone pair donors. They are not hydrogen donors. So amongst themselves, they cannot hydrogen bond. Let's go to the next strongest force, which would be the dipole-dipole force. Do these molecules have dipole moments? Indeed they do. The oxygen is much more electronegative than carbon, so electrons are pulled towards that oxygen, generating a dipole moment. And so therefore, they are going to have dipole-dipole forces as their strongest intermolecular force. Just like we talked about for alkyl halides, this is going to mean that these will generally have lower melting points, lower boiling points than alcohols, but higher boiling points and melting points than alkanes of a similar molecular weight. As for their solubility in water, we might expect very small aldehydes and very small ketones to be soluble in water, but once the amount of carbons gets substantially larger, they're not going to dissolve very well. For example, acetone will dissolve in water. That would mean we would have a CH3 here and a CH3 here. We'll encounter it in just a moment. But once we start adding more carbons beyond that, they become substantially less soluble. Now, the naming rules for aldehydes and ketones are very similar to alcohols, with a couple minor modifications that we need to add. So the endings of alcohols were OL. So the names of aldehydes are going to end in AL, al. Ketones are going to end in -one. Aldehydes must end a carbon chain, or to say it another way, they must begin a carbon chain. If we go back and look at their structures, you'll see that this is a carbon. We have a hydrogen here, oxygen here. So 3 of the bonds are already accounted for. So this has to be the end of a chain, because the carbons can only continue off to the left here. So therefore, aldehyde carbons would always be carbon number 1, assuming that there is no other functional group present. And we won't look at cases where there's more than one functional group. So therefore, we do not number the aldehyde carbon. It is understood to be number 1. When we get to carboxylic acids in chapter 13, we will see that the same thing applies to them. Ketone carbons must be numbered, although technically it's not necessary to number ketones with fewer than 5 carbons, because as you'll see, it will be understood where the ketone would have to be present just by looking at the structures. Unfortunately, aldehydes and ketones, along with some of the other compounds with carbon-oxygen double bonds, are going to have common names which we need to know. I'm going to try to keep that list as short as possible. Okay, so let's go ahead here and look at the names of these compounds. So we should be able to figure out the IUPAC names. So we have 1 carbon here. So 1 carbon, the parent name is methane, and we change the ending to match the functional group. So this is an aldehyde. Notice this is the 1 aldehyde possible, which has 2 hydrogens on that carbon. So methane became methanal. Now, almost no one calls this compound methanal. This compound is usually named formaldehyde. So the asterisk indicates I do need you to know that this is also called formaldehyde in addition to methanal. Its formula is often abbreviated CH2O. CH2O. Now let's compare these compounds. Here we have the aldehyde, which has a 2-carbon chain here. So instead of methanal, this becomes ethanal. The common name of this compound is acetaldehyde. It's not important that you know this common name, but you'll see acete coming up a lot. That generally means 2 carbons. Like, for example, acetic acid is derived from that. That's because this group right here, if we take everything here and ignore the hydrogen, is called an acetyl group. Not a fact you have to know, but you do see that in chemistry fairly often. How about here? Here we technically have 2 functional groups. We have a benzene ring, which means that this is an aromatic compound. And here we have an aldehyde. So this is going to be named simply benzaldehyde. That is both the IUPAC name and the common name. And now I'm sorry, earlier I did say that we would not be naming compounds with 2 or more functional groups. And the exception to that will be aromatic compounds. Those there will be some that we have to know how to name both. Moving down to the second row, these are all ketones. So this compound has 3 carbons. That is the minimum number of carbons that you can have to have a ketone. Why? You need the carbon with the double bond oxygen. You need a carbon on the left, you need a carbon on the right, so a minimum of 3 carbons. So this has 3 carbons. The parent name is propane, so this would become propanone. Again, this is a compound which is rarely known by its IUPAC name. This compound is almost always known as acetone. Acetone. You might ask, Professor Katroulis, shouldn't this be named 2-propanone? And I would accept 2-propanone as a name. However, there's not really a need to number this carbon, because think about this. If this double bond oxygen were over here, it would be an aldehyde. If the double bond oxygen were here, same thing, it would be an aldehyde. So it's obvious from the structure that we don't need a number to say that it's on carbon number 2. Same thing is going to apply over here. Here we've just added an additional carbon, so instead of propanone, this becomes butanone. I would also accept 2-butanone. We don't need to number this one, because if the double bond oxygen is here on carbon number 2, it's 2-butanone. If the double bond were over here, well, that wouldn't be carbon 3. That would now become carbon number 2, because remember, we need to number to make the functional group the smallest number possible. So just butanone would be fine. When we get to 5 carbons or more, we do need to number them. And if you want to number them, I'm more than happy that you may do so. Over here, is this a benzene ring? No, definitely not. Remember, a benzene ring needs to have the alternating pattern of double bonds, single bonds drawn in their structure. This is just a cyclohexane ring. So we take the parent, cyclohexane, and change it to cyclohexanone. As always, when there's one ring and one functional group, it is understood that the functional group is on carbon number 1. Hence, we don't have a need to number this. Here I have 3 aldehydes and or ketones that I would like you to assign IUPAC names to. They look challenging, but I promise you they're not terribly difficult if you go through the rules carefully. So I would like you to take some time, pause the video, and then we'll come back and look at how to name these. Okay, the first thing that we should do here is recognize the functional group that we have. So this is an aldehyde. Yes, I know I've typically drawn the hydrogen to the right. There's no such requirement that the hydrogen be written to the right. It could be written to the left. It means the same thing. And usually we do draw it in the correct angle, which would be 120 degrees, but it's still understood here that this is an aldehyde. So we want to find the longest carbon chain, which contains the aldehyde. So this would automatically become carbon number 1, carbon number 2, carbon number 3, and then either of these could be carbon number 4. They're the same group, so I'm just going to number left to right. So the parent hydrocarbon name is going to be butane with 4 carbons. The ending is going to be changed to butanal because of the aldehyde. And now we have to do the substituents that come at the front. On carbon 3, there's a chloro group. On carbon 3, there's also a methyl group. So we list those in alphabetical order as 3-chloro, 3-methyl butanal. Again, no need to ever number an aldehyde. And in fact, it would probably be considered wrong if you did so for an aldehyde. Now the next compound might look very intimidating because of all those carbons. But if you just follow the process of finding the functional group and finding the longest carbon chain, you'll see that it's not going to be really all that difficult. So let's highlight this one. So first of all, we have to have that carbon because that has the functional group in it. If we consider carbon chains, it's going to have those carbons over there. If we take a turn down here, then you'll see that this adds 2 carbons going here, 2 carbons if we went this way, 3 carbons going this way. So the longest chain goes across there. And so now you should see that naming this compound is not going to be all that challenging at all. We just have to count the total number of carbons that are in that chain, and we find that that is 8. So octane is going to be the parent. We need to number so that we get to the functional group with the lowest possible number. So going from the right, we'll do that, 1, 2, 3. Let's number. And then we have one substituent here on carbon number 5. What is that substituent? 3 carbons, remember, would be a propyl, but it's attached to the middle of the propyl, so we called that isopropyl. So this is going to be 5-isopropyl. We do have to say where the ketone is, because it could be on carbon 2, it could be on 3, it could be on 4. So 3-octanone. 5-isopropyl, 3-octanone. And finally, we have another ketone in a cyclobutyl ring. So if we're going to go ahead and look at this, this becomes carbon 1 automatically. It doesn't matter whether we go 1, 2, 3 or 1, 2, 3 for this compound, because either way you get to the 2 methyl groups on carbon number 3. So we have 2 methyl groups here, and so the substituents get listed first. 3,3-dimethyl for the 2 methyls, and then the rest of the name is simply cyclobutanone. I'm going to go ahead and stop this video here, and we'll pick this up in the next video with the important topic of oxidation and reduction reactions.